Okay, hey friends. So today I'm going to talk about libpthread and glibc and this optimization that everyone thinks is in libpthread that actually isn't, which is kind of an interesting story. So it has to do with condition variables. And so condition variables are kind of a low-level synchronization primitive where you can use them if you have multiple threads and you want some threads to wait on until some other threads do some processing or do some action. And then you want the waiting thread to continue after that signaling thread signals them. So, and here's how it kind of works. So you need three things for to use condition variables. You need to have the condition variable itself, you need to have a mutex, and you need to have some shared data that is protected by the mutex. And this is going to be the actual condition. It might be like a flag, like a Boolean flag or something, or like a counter. And so the way it works from the signaler's point of view is you first need to lock the mutex, then modify the shared state and set the condition, and then you can signal the condition variable. And this is going to cause the waiting thread to wake up and do its thing. And so this is actually kind of nuanced, and there's some controversy around exactly the best way to do this. Basically, the controversy is whether you need to signal while the mutex is locked, or if you could signal after the mutex is unlocked. This is actually a really nuanced question, and it's actually very controversial on the internet. People are discussing this, whether it's safe or not. The real quick answer is that for most cases, it doesn't actually matter too much. It's technically always correct to do it inside of the mutex being locked. There are some edge cases where maybe you can have undefined behavior if you do it outside, but those are kind of rare edge cases. But the other factor in deciding whether this is correct or whether you should do this or not is a performance reason. And so there is technically technically you can have worse performance if you signal within the mutex lock, and here's why. And so because it's because of the waiting thread and how that works. And so what happens with the waiting thread is basically it's going to grab the mutex, check the condition, and if the condition is not ready yet, it's going to unlock the mutex and then do a wait, which is going to put the thread to sleep and then wait for the signaling thread, basically. And so if the signaling thread signals while the mutex is locked, then the waiting thread is going to wake up, go to the start of the loop, try to get the lock, but the lock is already the lock is still locked by the signaling thread, and so it's going to just go back to sleep again because it can't get the lock. And so the idea is that this is a expensive and redundant wake, and it's not optimal. And so if you signal outside the lock, you avoid this because the signal is going to cause the waiter to wake up, and then it's going to actually grab the lock because the lock has been unlocked already. And so you don't avoid, so you avoid that unnecessary and wasteful wake of the waiter thread. But there's also this optimization, and that's where this optimization comes in. And so the idea is that thread libraries are aware of this and try to optimize when the condition variable is signaled inside the lock. And so what they're going to do is that if they detect somehow, I don't actually understand this part super well, if they somehow maybe detect that they're inside the mutex, rather than actually signaling the waiting thread to truly wake up on the signal, what the signal does is it actually requeues this waiting thread onto the wait list of the mutex. And so what that means is that the signal is going to happen, and then nothing is really going to happen with the waiting thread. It's just going to get requeued onto the mutex. And then when the mutex unlocks very quickly, that's when the waiting thread wakes up. And so the mutex unlocks, the thread wakes up, and then Then it goes and tries to grab the lock, and the mutex is unlocked, and so it can get it, check the condition, and keep going. And so basically, when I was learning about this, I was reading Hacker News because they were talking about this, and so they're talking about whether it's notifying outside the lock is better. Also, signaling and notifying are basically the same thing. The pthread uses the signal terminology, but the C++ standard library uses notify. But so they talk about this, that notifying outside the lock is better. They talk about this unnecessary context switch. Then this person responds, it's like, is this actually true? Aren't most implementations optimized to avoid this? And they keep talking about this. And then this person chimes in, the optimization you're talking about is called weight morphing. Linux futexes support this, and glibc did at one point. I'm not sure whether they still do though. So futexes are the underlying functionality that libpthread uses. And so they're like, glibc did have at one point, but I'm not sure whether they still do, which is kind of an interesting thing. That they weren't sure if it was still there or not. And so another thing I'll point out that's interesting is, so in this GitHub thread, Howard Hinnant, who is, I believe, the author of libc++, his formal advice is to signal while it's locked. Yes, notify default to doing it before you unlock. So signal, this is his advice, signal while it's locked. And his rationale, it's never wrong to unlock after, it's sometimes wrong to unlock before. So he's saying it's never wrong to do it this way. It can sometimes be incorrect and cause undefined behavior and stuff to do it this way. And so this is what you should default to. And he also adds, there's no performance penalty in unlocking after, as good implementations take this coding pattern into account. As good implementations being like libpthread. So he's assuming that this optimization is in place. So yeah, so that's what he's talking about. He's talking about this optimization. So let's actually look at glibc, libpthread. And so yeah, libpthread is inside of glibc in this thing called nptl, something thread library, I forget. But if we look at pthread consignal.c, so I actually don't really understand most of this thread. This function is not very long, but just take my word for it that there's nothing here that really suggests there is this optimization occurring. They don't really mention it anywhere. I couldn't find it anywhere. And so from everything I could see, it suggests that this optimization is actually not in place in glibc anymore. And so now the kind of question is, well, what happened to it? Was it ever there, or why did it get removed? And so we can just check out the git log. It's pretty interesting because there's basically no activity on this file for 4 years, going back until 2016, where they talk about this new condition variable implementation that, I don't know, changes stuff. So they talk about all this stuff that I don't understand, but this is what stood out to me. This condition variable doesn't yet use a requeue optimization. And so so this is interesting. This is actually the optimization that we're talking about here. So the person on the Hacker News called it weight morphing, but I think requeue optimization is actually the more technically correct term. So they're using it here in like the dev actually uses it, but also it's actually the name of the futex operation that you use to implement this optimization. So it's called futex comp requeue. And so I think weight morphing is not actually the greatest name for it. I kind of wish I knew that earlier. But they talk about how this conveyor doesn't yet use the requeue optimization, which is really interesting. And so basically, they revamped libpthread and the signaling or whatever, and didn't add this optimization back into it. So what we should do now is we should actually check out to right before that commit and look at the file. And if we do that, it's pretty immediately obvious. They talk about futex comp requeue, and they talk about requeue, and I don't actually really understand these internals and these details, but it's obvious that something is happening here with the futex requeue, which to me suggests that the optimization was there. And so basically what happened is glibc had this optimization and everyone assumed it was there, and then glibc actually got rid of it and people don't seem to be aware of this, including I guess the creator of libc++. So everyone assumes that it's still there, but it's actually not, which is pretty fascinating. So that's pretty much it. Hope you found this interesting.